We're here to talk today about a new tool called Metal³ that is specifically designed to provision nodes in a Kubernetes cluster. And I'm going to give a little bit of background about the project and talk a little bit about the design, and then Russell's going to do some demos for you. So the first question I'm sure all of you are asking yourself is, why did we build another tool to provision servers? There's a bazillion tools out there already that do that, and we've been doing it for years and years, and what is the point of having another tool? So we had three main reasons that drove us creating this new project. The first is that we wanted something that had a Kubernetes-native API so that a kubeadmin who was working with their cluster could use the same tools to administer the infrastructure underneath the cluster that they use to administer the applications that run on top of it. We also wanted the tool to be self-hosted so that it would run in the cluster so you don't have to deploy something separately in order to manage your clusters. And then we also wanted the tool to manage the cluster itself. So we've tied in with the machine API from SIG Cluster Lifecycle so that once you have the tool installed, everything works just the same way it would as if you had a cloud-based cluster. So you're operating your bare metal cluster in the same way that you would if you were on Amazon or Google or whatever. So let's look at the pieces of the system, talk a little bit about the design and how it works. I mentioned that we wanted to have a Kubernetes-native API. So the API for Metal³ is a new CRD called the bare metal host. And that gives us a little bit of information about the host so that we can manage it. So we need things like the credentials and the location of the baseboard management controller, and then some information about it so we can recognize it when it shows up on the network, so we get things like a MAC address and stuff like that. That information is used by the bare metal operator, which drives the provisioning process by invoking the Ironic REST API. So Ironic is a provisioning tool that came out of the OpenStack community. It's got a nice REST API for doing provisioning, and it knows how to work with a lot of different kinds of hardware. And by adopting that, we were able to really bootstrap the project and make a lot more progress than if we had started from scratch. Ironic is deployed with Metal³, so you don't have to stand up a separate set of Ironic services. You don't have to manage that. It's all managed as part of managing Metal³ itself. Ironic will use the image that you have hosted in your image registry, and it will take some config drive data that we pass it, and it will deploy the image to the server and reboot the server to run whatever that image is. So this this layer of the components is basically a generic provisioning tool that wraps up an existing API in a Kubernetes native API. So that gives us two of our three goals. We've got that Kubernetes native API, and it's self-hosted, running in the cluster that you're working with. And in order to meet our third goal of having it be self-managing, that's where we tie in with the machine API. The machine API is out of the SIG Cluster Lifecycle group. It defines things like machine set and machine, which allow you to, they work kind of like deployments and pods. It lets you scale up your cluster using different criteria. And so we've implemented a provider that plugs into that, looks for machines that specify that they want to be bare metal machines, and then the actuator knows how to take that information and configure the host and drive the provisioning process so that it becomes a node in your cluster. All right, so I've mentioned three different representations for the same sort of piece of your cluster. We get this question a lot. Why do we have nodes and machines and hosts? Nodes, I'm sure everybody's familiar with that concept. That's the basic concept built into Kubernetes of basically where you have a kubelet running. The machine is the new thing that comes from the SIG Cluster Lifecycle group and the work that they're doing there, and think of it as a request to have a kubelet run somewhere. And when you're running in a cloud environment, what happens is the provider calls out to the cloud API, creates a new instance, configures that instance to become a node, and then uses the machine resource to keep track of the instance and track the information about it and that sort of thing. Well, in a bare metal environment, we don't have a cloud API. We have to become the cloud API, and so that's what the host resource is for. That gives us that API that we can call out to and trigger provisioning, trigger configuration. And the host resource becomes inventory, so you're tracking all of your inventory that's available to your cluster at the same time. So let's look at the details of what a host actually looks like. I mentioned that we need the base management controller credentials and location, so that's here in the BMC fields. We support a couple of different kinds of BMCs for different hardware vendors. So there's the URL specifies what protocol to use, and then a location on the network where we can find it. And the credentials are stored in a secret so that those are all protected, and we just read the secret inside the operator when we need it to talk to Ironic. The consumer ref field is used to keep track of which hosts are actually being consumed by some other system. So in this case, it's been allocated to a machine, so it's going to be provisioned, or it has been provisioned as a worker node in this cluster. If you were using the lower level API yourself to provision other things, you could put some other reference in there just to sort of keep it as a placeholder to indicate that that host is being used. The image fields control what image has actually been provisioned to the host. So if you want to re-provision the host with a newer image, you would change the URL there, and that would trigger re-provisioning, writing a new image to that disk. And then the user data field points to a secret that contains information that we pass to config drive, so that during the boot process, you can inject your SSH keys or anything like that. And we use that within OpenShift to inject the ignition configuration data. So that's the spec section of the host. The status section includes some information that we can learn about the host as we inspect it and do provisioning. So the hardware fields collect information about all of the CPUs, all of the network interfaces, all the storage that's available. I've abbreviated this. We actually collect quite a lot of information that's available about what's in the host. And you can use that to select which hosts you want. So you can select only hosts that have a certain amount of RAM to be a part of certain machine sets and things like that. The operational status field is basically an error indicator. If we can't talk to the management controller, or if the machine suddenly stops working correctly in some other way, we're going to reflect the error in that field. And then that provisioning section at the bottom is showing what actually was provisioned to the host. So you have the instructions in the spec, and you have the actual reality in the status field once the provisioning is completed. And you will see in the demo that as the host is being provisioned, the state will update from different steps along the way to show exactly what's going on. All right, so at this point, I'm going to hand over to Russell, and he's going to talk about the deployment process and show some demos of deployments.
Sure. I've got 4 demos I'm going to show, and before I get into that, I'm just going to talk through a little bit, kind of wrapping up what Doug talked about. He talked about the architecture, some of the APIs. This is one particular use case. We've taken our Metal³ components we've built, and we have them integrated into to OpenShift. And so talking about what does that look like in an OpenShift cluster. So the use case, we have an existing cluster. We want to add another host to that cluster. What do you have to do? First, you got to set up the host. So literally get a physical host. You got to plug it in. And we have some expectations about how it's going to be plugged into the network. You have your primary network for the cluster. We have a separate provisioning network. So you get it set up. And then you're going to create that bare metal host resource. That's adding it to the inventory. So telling the cluster about a new host it has available to it to manage. And so to do that, you create the bare metal host resource. Then you're going to create a machine. So if our desire here is to enroll this new host as a node in the cluster, you need to create a machine. So maybe you create that machine directly, or you scale up a machine set, however you do it. And that's the end of your sort of active involvement in that. And then our automation kicks off from there. So once the machine gets created, it finds an available host to satisfy the request. It triggers provisioning. The host is provisioned, given the necessary configuration it needs, and it comes up and joins the cluster as a new node. Post-deployment, we also look at doing active monitoring of the state of the host, watching power state, also gathering any sort of looking at gathering out-of-band metrics, those sorts of things. So we're also looking at day 2 operations. And from there, I'm going to jump to a terminal and play a few things for us. So I'm going to go, like I said, I'm going to go through 4 demos to show different aspects of this. And the first one is inspection. So let me talk a little bit about the environment that these demos are running in. So in the project, in the Metal³ project, we have a repo called Metal3 dev-env. What this development and test environment does is it sets up a an environment with virtual machines, and we're able to manage and provision virtual machines just as if they're bare metal. So that's what you'll see here. It's handy for for development and testing, and so that's what I'm using here to show these. And the inspection process. The inspection process is the process that we go through to gather all that hardware detail. So when Doug showed the status section of a bare metal host and all the information about the hardware, that's what inspection is. So I'm going to show that happening. So we're going to kick off play, and the first thing I'm going to show here is that this is a cluster that has no bare metal host resources created yet, so I'm about to create them. And in here we've got two, a host 1 and host 2, and the required information. We need the MAC address so we can recognize these hosts in the provisioning network, and we need the BMC information, its IP address and the credentials and a secret. And I'm also creating 2 secrets with those credentials in it. So here we go, we've created those 2 bare metal hosts and the 2 secrets. And now I'm going to watch looking at the bare metal host resources. So here we are, we've got our 2 hosts, and they've just been created, and you can see the provisioning status is in inspecting. So what happens here is the first thing we do is we boot these hosts into a special RAM disk. This is a capability of Ironic. This RAM disk then runs some tools to gather all the data about the hardware it can find. And then it posts all that hardware details back to an API so that we can store it and present that in the bare metal host resource. So through some of these things that are normally long-running operations, of course, I'm speeding up the recording here to show, but that finishes and it gets into a ready state. What's in a ready state, that's a host that is ready to be provisioned for some purpose. So I'm going to jump out of that, and I'm going to look at the YAML of one of these resources and show that now it's populated with all these hardware details. So I'm going to scroll on down, and here we are. So now the first, this is our CPU section. The thing on the slide earlier was abbreviated, and this is sort of showing more of the details. So the architecture, speeds, how many CPU cores we have, all the CPU flags that you might care about to know. Scroll on down. We might gather a bit of firmware information. We know the host name of that host, the host name it got when we booted that RAM disk. What host name did it get from DNS? We store that off. What network interfaces we observed on the servers and what IP addresses they got. How much RAM it has, how much storage we had. In this case, this is the VM test environment, so it's got this one disk. And any sort of bit of BIOS information we can collect. So all that's at least this is a sample of what we would get in our VM test environment. And all we had to do was create that host and give it the credentials and IP address for that management controller. So that's the step. So now we're going to, so far I'm only looking at the bare metal host API. The next thing you can do, if you're only focused on the lowest level API here, the bare metal host, you can provision an operating system image to that host. And so that, we know how to take an image and get it written to disk and then have the host reboot back into that image that we've written there. So I'm going to show that process. And what I'm going to do here is I'm taking the generic CentOS cloud image that you could download from the CentOS website and get it provisioned here. I'm passing enough user data so that CloudInit can inject my SSH key, and I'll be able to SSH into the resulting provision server. So off we go. So we have those host 1 and host 2 that I created in the last demo. I'm going to show here in this host, if we go down and search for image, this is down in the status section, showing that in the provisioning status, there's no image, so it's not provisioned with anything. We have not provisioned anything to the disk of the server at this point. And so to trigger provisioning, what we need to do is specify an image in the spec of the bare metal host. And that is what we will do next. I have just a little helper script that'll do that. And it'll do 2 things. It's going to patch that bare metal host to specify an image, and it's also going to create a new secret, and that secret contains the user data. And again, if you've used any sort of compute infrastructure API, it's common that you can pass this sort of data that, on first boot of this new server, a tool like CloudInit or Ignition can then take this and initialize itself. And so that's what we support that through this API as well. And so that's what this secret contains. It contains, in this case, data for CloudInit to inject my SSH key. So I'm going to take a look at this bare metal host resource again and show that we've patched it and set an image. So here we are. And it's this is the generic cloud image from CentOS, unmodified. but hosted somewhere in the cluster so that it can download it faster. And once we back out here, we can look at the bare metal host resources again and see that it's in a new state. So now that we've patched it and set an image on this bare metal host, it's now in a provisioning status. So we can watch this, and of course, this is a fast-forwarded recording, especially on real bare metal host. This takes a bit of time because we're rebooting the servers a couple times to go through this process. But what's really happening in the background is we're telling Ironic to drive the deployment process. We're booting the server into a RAM disk that's a part of Ironic that knows how to then pull down the image and write it to disk. And then we ultimately reboot the server into the operating system we wrote to the disk. So there we are. It provisioned itself, and I'm showing here just as a reminder, in the status section, we happened to gather some IP addresses for the network interfaces before. And so I can snag one of those and SSH into this new server that I just provisioned to kind of demonstrate that it really did what I wanted it to do. All right, grand. So we SSH'd into a new CentOS host, ran uptime. It's been up for 0 minutes, so this is a freshly provisioned host. And of course, like I said, the only thing we've done here is injected an SSH key, but it kind of shows that at this base layer of the things we've built, we've provided this Kubernetes-native API for getting operating system images provisioned to bare metal hosts. So that is that. And of course, you can do the opposite. You can deprovision a host, which is similar, and when we provisioned it, we patched it to set the image. If you patch it and remove the image completely, that's saying that now your desired state of this bare metal host is that nothing is provisioned to it. So then we will drive it through a deprovisioning process and wipe the disks, and off it goes. So that's what this will be. Goes into a deprovisioning process, and it's back to a ready state. And this is kind of back to where we started. Now this host is ready in the inventory to be used for some future purpose. Okay, demo number 3. So I kind of talked to this a little bit before I jumped into the terminal. What does this look like in OpenShift? We've integrated this into a platform and using the machine API. I'm going to show that process I talked about a little bit, where we have an existing cluster. I'm going to start with a cluster that has three masters, and how do we what's the process of adding a new host to become a worker in this cluster? So that is this. So first, I'm going to take a look at some existing resources we have. There are 3 masters. There are 3 bare metal hosts that correspond to those 3 masters that exist. And there's also a machine set. This machine set represents the number of desired worker nodes for this cluster. And right now it's set to 0, but we want to add a worker. So what do we need to do? The first step is we need a bare metal host in our inventory that can actually be provisioned. So we've got to create another resource here. So that's what we have here. It's got the IPMI address and credentials and a secret, and I'm going to create that. All right, so we've created that new bare metal host, and if we look at the list of bare metal hosts, we had those 3 masters before, and now we have a 4th. This 4th one is in a ready state. It's ready to be provisioned. It hasn't been provisioned yet. Nothing has told it to be provisioned. And you can see there's a machine column. The 3 masters are associated with the machine for those 3 masters. That 4th one's not associated with the machine yet. So what we need to do next is go back to that machine set that represents the set of worker nodes in our cluster, and we're going to scale that up to 1 to say now our desired state of the cluster is that there's 1 worker. And when that machine set gets scaled up, then a machine resource will get created. And when that machine resource gets created, our machine actuator will go and look for a bare metal host that's available that matches the criteria we've set, and it will kick it off to be provisioned. So here it off. Of course, now the machine got created when we scaled up the machine set. We can see in the bare metal host list that it's in a provisioning state now, so this is now getting provisioned. And it'll be given the user data it needs to then initialize itself and join the cluster. I'm going to watch a few things. I'm going to look at not just the bare metal hosts and then the nodes of the cluster so that we can see when the new worker joins. I'm also looking under the hood a little bit. We've mentioned before that we're using Ironic under the hood as the provisioning tool to do the work, so I'm looking at the state of that. You can see that it's the bottom, in the first section there at the top, the bottom host is the new worker that we're provisioning. First, it's going through this cleaning stage. Cleaning is where we boot up a RAM disk and make sure the disks are cleaned. We're like wiping the disks to ensure that that there's no stale data on there from previous use of the host that we don't want there for this next use. So it goes through this cleaning process, and then after cleaning is complete, we go through the deployment process where it actually writes the desired operating system image to disk. And once the deployment is complete, it's going to reboot that host so that it boots into the image that we wrote to disk. And once it's finished initializing itself, we'll see it join the cluster, and you'll see it appear in the list of nodes there at the bottom. So it just went to active and provisioned, so that host now is provisioned. And so what it's done is that it's rebooted it at this point, and so you wait a little bit more time for it to boot, and then initialize itself, and then here it is, it joins the cluster. And not ready, and then after a little bit more time, after it fully initializes itself, it is a ready node for the cluster. And that is the workflow for a bare metal cluster with OpenShift, how to add a new host. So you gotta create, just to kind of recap there, we created a bare metal host resource with the management controller, IP address and credentials, and then we scaled up a worker machine set. That was basically the 2 steps. Okay, that's demo 3. Demo number 4. If you're familiar with the cluster API group out of SIG Cluster Lifecycle, a newer version of this API is V1 Alpha 2, and I'm going to show a demo of using that API here. There's a team from Ericsson who's been working really hard on V1 Alpha 2 support, and they helped me get this working, so thank you very much to that team for their hard work on V1 Alpha 2 support, and of course helping me get this demo prepared. So I'm going to show provisioning a new cluster. So this is a different environment. We showed before the sort of self-hosting this components and provisioning new nodes for like your own cluster. And this is a slightly different approach where we're starting with a Minikube cluster. And this Minikube cluster is your management cluster. And then we're going to provision 2 new hosts to become a new cluster. So we're going to provision a new worker and master to become like a new cluster. So that's what this is showing here. So first step, just to show what's running here. So just to recap what's running, this pod at the bottom, this is showing the pods in the Metal3 namespace. The pod at the bottom, Metal3 bare metal operator, that's the bare metal operator from the Metal³ project. And Ironic runs within that pod as well. There's also the generic cluster API controllers. The CAPBM part is the cluster API provider, bare metal. And then the very top one, CAPBPK, that's the cluster API bootstrap provider kubeADM. So, and that is going to take care of provisioning the cluster after we provision the host. It's going to configure the cluster. Okay, so that's what's running. I'm going to run a few scripts here that exist in our development environment that you can try out if you wanted to try this out yourself. And it's going to create a cluster resource, and it's going to create the machine and related resources needed to provision both the control plane, or the master, and also the worker. So now that all the necessary resources have been created, I'm going to take a look at watch some resources. So I'm showing here both machines and bare metal hosts. And so there's the 2 bare metal hosts that represent the master and the worker, and then the 2 machines corresponding to that. So the way this process is going to go through is it's first going to provision the control plane, or the master, and it's going to make sure that's fully up and running before then it provisions the worker associated with it. And so once the master is fully provisioned, there'll be another section I've added to the output here that's talking to the API of the new cluster getting created and listing the nodes of this new cluster. So now here the master is provisioned, it's booting up, and now once it's up and running, I can talk to the API of the new cluster and see that it has a master. And we let it go a little bit further, and now it's going to provision that worker for us. And after the provisioning of that worker completes, we will see a worker appear in the nodes of our new cluster. And what's really cool about this, an earlier iteration of of the cluster API, the work to use kubeadm to configure this was a little bit more coupled to the infrastructure provisioning. What's cool about this version is that's better decoupled, so we're able to reuse this bootstrap provider that runs kubeadm on top of our code that just knows how to provision bare metal hosts. So there we are. We've got a new cluster with a master and worker. I'm going to run a couple of commands just to kind of further prove that we've got a new cluster here. Going to show the pods running in our management cluster, and then I'm going to connect to the API of the new cluster and show the pods running there, and you can see, of course, that they're different. So the first command here, well, actually, first I'm showing you can get I'm using a libvirt command to get the DHCP leases of our different hosts in this development environment, so I know how to SSH into the master of our new cluster. But when I read this first kubectl command, this is the management cluster. This is our Minikube cluster. You can see that it has the kube system namespace and then our Metal3 namespace. And now I'm going to run the same command, but SSHing into the master of our new cluster, and we'll see that it's got an independent set of pods running there, and showing that we can talk to an API of a new cluster. And that's the end of the demo. So we have our, we started at the ground up how to use a Kubernetes-native API to provision hosts. We layer on the machine API or the cluster API on top of that for managing Kubernetes clusters. And we've integrated that into OpenShift, and we also have support for V1 Alpha 2 and that you can go try out. So thanks again to that team for all their great work. And that is the end of our demos. Let me jump back to the slides here. Those demos are not published on the blog yet, but that's where they'll be after this if anyone wants to see them. On our website, there's a blog, and I'll get them posted there. A little bit of commentary on future work. So what's happening? Of course, I've talked about the V1 Alpha 2, and then there's V1 Alpha 3 happening. So we're going to continue chasing that as a community to continue to improve our support for those APIs. Also looking at just continuing to improve our ability to manage bare metal hosts. There's active work happening to manage BIOS settings during deployment, also active work to do RAID configuration. So those are some of the active things going on. And so with that, we can take some questions and say thank you for coming to listen to us today. And of course, thank you to the people that have been contributing to our community so far. It's been a pleasure. So thank you very much. Now we're gonna pass the microphone around for questions. So like raise your hand and kind of get the attention of Robert to pass the microphone to ask questions. And we will use the rest of our time which is about 5 minutes, I guess. Okay.
So is there a way to auto-register a bare metal host, like on Pixie Boot or something like that? Like, I see you were creating the resources, but could I have it so that it just makes them for me?
Yeah, great question. So is there a way to automatically register bare metal hosts instead of having to create the resource? It's kind of like one of those things that's on the roadmap, so I don't think we've fully integrated that yet. Ironic, our underlying provisioning tool, does have discovery capabilities, and it's kind of been one of those things. I'm sure we have a GitHub issue filed of like we need to finish getting that integrated. The idea was leverage Ironic's discovery capabilities, and when Ironic discovers a host, we can sort of mirror that back up as a new resource. We haven't implemented it yet, so it's like feasible, not done. Yes.
Hi. Are you using this to provision all the bare metal hosts, not just for Kubernetes, but for everything?
So are we using it to provision everything? It can be used that way. I mean, our use case, so I have my upstream hat and my Red Hat hat. Our primary use case, we're very focused on provisioning nodes for Kubernetes clusters. Now, the bare metal operator as an underlying key component or piece of technology, we designed it with that in mind. Like, it just knows how to provision operating system images to hosts, and you could use it for anything.
It doesn't know what they're for.
Yeah, the bare metal operator at that layer, it doesn't know what you're doing. It just knows it's provisioning images to hosts. Of course, our primary use case has been Kubernetes nodes, but it could be for anything. Cool.
Once Ironic has detected and discovered the device, when it's in that ready state, is the machine powered off and just waiting for IPMI boot, or is the machine like sitting in a RAM disk? So let's say I have a bunch of machines that are provisioned and I just want to leave them in that state. Can I leave them off my DC and then just power them through IPMI when I need them?
Want to take that one?
Yeah, so by default, it stays in a running state, and we're collecting out-of-band metrics so that you can see, if your unused nodes are overheating for some reason or something like that. There is one of the fields that we didn't show in the spec is actually a power switch, so you can turn it off using the CRD.
So the bare metal host CRD is a declarative model. It is saying that the version of the OS should be X, but if somebody goes and patches the version of the OS to be X.2, what happens? Or are we planning to have a patch process in the CRD itself?
So I think the question is, we've got, when you provision an image, that image is a particular version. What happens if you bump that version, that sort of thing? So this is sort of a layered system. If you change that image on the host, we're literally going to reprovision the thing. That may be what you want. It's also likely not what you want. Once you have it provisioned, you probably want to just do it in software in management of the running host to update the operating system. So I probably wouldn't design my workflow such that every time I'm doing an OS update, you can reprovision it from scratch every time, or you could leave it running and update it in a running state. But it's sort of left up to you. That's at the bare metal operator level. It's sort of, we can reprovision at your demand, left up to some higher level system to decide how to do that.
Yeah, it uses whole disk images, so it doesn't do smart upgrades. Yeah. So it's literally going to wipe the drive. You'll lose whatever is there, and it'll lay a new image down.
Yeah.
Question about dependencies, two sorts. In follow-up to your answer to that guy's question, I'm wondering now about circular dependencies. This thing is running on a cluster and managing the cluster that sounds kind of circular. Also, you mentioned you're using Ironic. How much of the rest of OpenStack gets dragged in with Ironic?
I'll answer the second question first. How much of the rest of OpenStack? Nothing. So we've sort of we've minimized it, and we even have Ironic running in a special way that it's not using RabbitMQ, for example, if you're really familiar with the architecture. So we've got it running in a very specialized mode just for this, and we're not plugging in any other dependencies. And the fact that we're running it under the hood, these APIs are not exposed outside of the pod at all. It gives us some flexibility on how we manage it. So that's the second question. The first one, hey, it seems circular. We've got a cluster managing itself. How do you get into that state? Yes. The way you do that is you do have to start with something else. You have to get the cluster up and running, and then you can then move the components into the cluster. So in that last demo, V1 Alpha 2, that's not actually self-hosting it, right? That showed a management cluster that provisioned it. Like in OpenShift, we do things a little differently where we have an installer that runs a process to get the cluster up and running just enough, and then we move the components into the cluster. So you get just enough running, and then it moves into the cluster, if that makes sense. There's sort of a bootstrapping process that gets you there. So it's not magic. It's just it's a sort of a bootstrapping process that gets you up to a running cluster with the components running inside of it.
What happened when the machine being provisioned fails? So let's say hardware failure or the driver got into kernel panic. Would the bootlock get fed into Metal³, or are there any indications?
So what happens if the provisioning fails for some reason related to the host or something like that? The operator will keep retrying to provision. Eventually, the host will go into an error state that just reflects that it's failed to work. And so the actuator may choose a different host if you've got multiple hosts available in your inventory. If you're using that low-level API directly, then whatever tool you're using to watch that resource, the host resource, should be watching that status to see that it's got that error state.
Is there a cloud provider for Ironic, or did you have to write one for this?
Is there a cloud provider for Ironic? So we haven't needed to write a cloud provider yet. We've gotten by without having to write one. And we've talked about it a couple of times, but it hasn't been necessary. So, and if we did, it wouldn't be an Ironic one. So kind of as much as we're thankful to have Ironic because it helped us get going so fast with this project, Ironic is intentionally hidden Like so it wouldn't be an Ironic cloud provider, it'd be a Metal³ one, and it wouldn't have any knowledge that, ideally, like one of our architectural goals is there's no knowledge that Ironic is here outside of the internals of how we've implemented it. So it'd be like a Metal³ cloud provider potentially that does some bare metal specific things, but we haven't written one yet.
Do you have a plan to implement pivoting function, pivot cluster API controller managers into the new created clusters?
A new API to create what? I'm sorry?
I think cluster API version 1 have a concept to pivot into pivot.
Oh,
yeah.
Sorry.
Pivot cluster API control managers into new created cluster.
Yeah, so I think that's the work that you were showing with the newer version of the cluster API. So for the V1 version, V1 Alpha 1 version that we supported initially, we don't do any of the pivoting. It's just the self-hosted, bringing a node into the current cluster thing. But in the V1 Alpha 2 work that the Ericsson folks have been doing, then they are able to provision a separate cluster and pivot into that cluster. Yeah.
All right, and with that, we are out of time. I want to thank everyone for coming. If you please would rate the session on sketch.com, we'd really appreciate it.
Thank you very much.
Thank you.